Good morning, friends. In the previous video, we saw that using features with composition OMS, we were able to achieve the latency of 3 seconds. What it also means is that, so suppose if there are 12 concurrent client requests coming at the same time, that's what we mean by concurrency, that there are 12 concurrent requests from the client, each sending us 12 orders, one orders each. So we have got 12 requests, 12 client orders at the same time. We are able to process all of them in 3 seconds. So 12 requests sent to the downstreams, 12 orders sent to the downstreams per 3 seconds. So this is a great improvement overall. So let's revise that what are the approaches that we have taken using the platform threads or the native threads that we have been using before. So as per our problem statement that whenever we receive a client order, our server should proceed with all these steps. It has to parse the request, create an order from the request, validate the order, enrich the order, and update the orders to the persistence, and then finally send it to the downstreams. And I mimicked it that each of these steps will take 1 second each. So if it's like one request, it will take 6 seconds if all done sequentially. So that's what we learned about the single-threaded OMS, that if there's only one thread serving one order at a time, so it will take 1 second each, so it will take total 6 seconds. So if there are 3 requests coming at the same time, the other 2 requests have to wait, and that's why the overall time taken to serve 3 requests would be 18 seconds. Because it's all sequential if we are using single-threaded. Then we came up with this thread per client approach, because each client request or each order that we receive from the client is independent of each other. That's why we can create whenever we receive one client order, we create a new thread, and that thread would take 6 seconds each. But the benefit of using this is that if there are hundreds of clients sending the same order at the same time, all can be handled by 100 threads concurrently. But there the problem was that there is a limitation of how many threads that we can create, because as we learned that all the platform threads that are created, that are one-to-one mapped to the OS kernel threads, and those OS kernel threads are limited in terms of that how about the hardware and the OS that we are running on. So there would be only limited number of OS kernel threads which are there and which can be mapped at a time to a platform thread. All the other platform threads which are created, they have to wait until there is a context switch happening, so that the new platform thread can take over the kernel thread and then take over. But we already saw that these context switches are very, very expensive. So we try to improve this by actually so first of all, we are taking 6 seconds, so we try to reduce this latency of 6 seconds by concurrently running these 3 operations at the same time. So if we do 1 second each to 2 seconds, but if we can run concurrently these 3 parts, like validation, enrichment, and update to the persistence, if we can do all this in 1 second each, so we were able to reduce the latency. So we tried all these issues. First of all, the number of threads that we can create. So we tried with thread pool based OMS. So in that case also, there is a limited number of threads which can be created in the pool, so that we don't actually breach the limit of the number of threads that we can create in our system. So using all these approaches, we saw that although we can improve the latency from down to 6 seconds to say 3 seconds, but still we saw that there's a limited number of throughput that we can provide. Throughput means that if we have having hundreds and thousands of client requests at the same time, how many of them can be served concurrently, taking each of them 3 seconds each. So if we have got, let's say, if we are able to handle say 1,000 of client requests at the same time, so it means that our throughput is 1,000 client requests per 3 seconds. So this is what we want to improve by using virtual threads. So as we have seen in our previous videos that virtual threads are very lightweight. We can create a lot of virtual threads without having any limitation on the number of threads, on the number of OS kernel threads that are there, because there's not one-to-one mapping done on virtual threads, that how many threads it can be limited on if we have got very limited number of OS kernel threads. I think this we have already we have gone in details in our previous videos. So let's try to implement this benefits of using virtual threads in our OMS design. if I take the best two parts, I mean the second part here, the second approach, in which we are dealing with the thread per client request. So whenever we receive a client request, we create a new thread. The only limitation was that it was we cannot create a lot of threads, and that's why if we have got tens of thousands of clients sending us the request at the same time, then we saw that there were errors, stack flow error, or like no thread creation was errors, because our threads were exhausted. We could not create more number of threads. If we can limit this, I mean, if we can improve this by using virtual threads instead, because we have seen that we can create tens of thousands of virtual threads without any issue. So we can use this approach first, and also we can use this approach of it will take still take 6 seconds. We can improve this by running these three operations: validation, enrichment, and persistence in parallel. So it means it should take like 4 seconds, like one second each. These two, like 2 seconds, and then third second for taking all these three in concurrent way, and the last part to send to downstream. So it should take 4 seconds. So this is what we have implemented here in the third part. So if I combine this second and third part, the approach, but instead of using platform threads, if I use virtual threads, then let's see that how it will handle. I mean, how we can improve the throughput. So for the second part, third per client request, we had this design before, thread per client OMS, in which whenever we receive any accept connection, I mean any client is connecting us and sending us a request, we are creating a new thread every time. Okay, so this is our the first approach, and the second part was regarding using this part, third per client and thread per order parsing OMS, which means that we have multiple threads for order parsing, validating, and persisting and sending. So what it also means is that, I mean, this is what we have designed here, that whenever we receive the client request, what we are doing is that we have got multiple threads for doing the three parts, like which is validation, enrichment, and persistence, this is all done by several threads concurrently. That's why we are able to reduce the latency from 6 seconds to 4 seconds. So if I just combine these two, that's what we get here in this implementation. So let me go through it. It's very much similar, but the only thing is that now we don't have any thread pool, because there is no concept of a thread pool when we are using virtual threads. And so let's go through it, so code first, and then we will run some examples. So here it's exactly the same, that we are actually maintaining a client counter, that how many clients that we're going to connect, so that we can actually do some benchmarking. And then we are listening on this port 8080. And unless the server socket is closed, I mean, once we shut down the server, till then it will going to accept it. It blocks, and socket can never be null. Okay, so whenever a client is sending a request, only then we will get a new socket object out of it. And at the same time, we'll create a new thread, a new virtual thread. This is a design, Thread.startVirtualThread. I think we already went through the examples before, but let's revise it again. So here we are passing a lambda, and then we are handling it inside this virtual thread. And after that, our main thread, which has been listening, it will go back here. It is not closed yet, and then it will accept for another socket connection or another client accept. For the handling part, again, we are going to use virtual threads. So what we are doing is that we are actually creating like a request out of the socket, like 1 second. Then we'll get a new order from the request, which is another order that we are going to use to validate, enrich, and persist. And this is a concurrent part. So we're going to create these three virtual threads at the same time for validation, enrichment, and persistence. And once we get this back, then we are running this in parallel. And then our main virtual thread is being joined here. Unless these three operations complete, validation, enrichment, and persistence, only then it will send the order to the downstream. So this is a very simple design, first of all. I mean, if we have seen the previous features with composition and callback, I think this design is much clean and easy to understand as well. Every time we are creating a new virtual thread to handle, and then we are running these three operations in parallel, so that we reduce the latency from 6 seconds to 4 seconds. So here, as again, we are combining these two approaches that we have used before. One is thread per client request, or virtual thread per client request now. And we are using multiple virtual threads for doing some of those steps in a concurrent way. So let's see whether our design is good enough. I will run this, and then I will try to send the orders in thousands and thousands of times, and let's see whether our code breaks But theoretically, it should not break because virtual threads are very lightweight, and as you've seen that it should be able to handle lots and lots of client requests at the same time. So I'm running this now. I will just click on this main. You can also use Ctrl Shift F10. So once it is running, so it's listening on port 8080 as expected. Now it is going to, let me start with first socket client with like 4 connections at the same time. So if I just click this, we expect that it should take 4 seconds, right? So, and there would be like 4 virtual threads created immediately for 4 client requests, as you see that, and each of them is taking around 4 seconds as expected. And it was like very, very fast. As you can see that it's as soon as it's got, it's like all 4 requests serve at the same time. So now let's do some other stuff. I mean, we tried our thread per client request before. I mean, and then we saw that if we are like using 10,000 clients requests at the same time, then our server was unable to handle it because it was unable to create so many of platform threads. But now in this design, because we are creating virtual threads instead of platform threads, it should work. So okay, so I'm maintaining say client 1, 2, 3, 4, right? So let me actually now connect using 10,000 at the same time. So let me run this. So our virtual thread handler is still running. So as you can see now, we are simultaneously sending 10,000 requests. And here you can see that it's running at a very, very fast pace. And each of them would be taking only 4 seconds. So that's the benefit of using virtual threads. Virtual threads can create lots of threads, and the way that it handles the way it actually mounts over our see, you can see that it's already done 10,001. So, and here we can see that it's, while we're talking, I didn't do any pause here. It was all done at the same time. And if we look for any request here, we will see that all of them are taking 4 seconds. There has been no change in the latency, and it was able to handle 10,000 requests almost at the same time. So here, I mean, we can also increase our socket client request from 10,000 to like even 20,000, 30,000 and all. And I tested it with various examples. You can also test it. The same example code that has been given here. You will see that virtual threads are able to handle so many number of client requests by creating virtual threads on demand. As soon as we have got a new client connection, it will create a new virtual thread, and it should be able to mount it on platform threads. The underlying logic for mounting and unmounting on the platform threads is so fast, and that's why it is able to handle so many virtual threads at the same time. Now, if we analyze this program again, the main difference that with using traditional thread is that virtual threads do not entail any OS level blocking. When a virtual thread invokes join also on a thread that is still running, it does not block the underlying OS thread. So it is independent of the underlying OS kernel thread. What it's only does is that it only mounts and unmounts from the platform thread, which has already been having like one-to-one mapping with the OS kernel threads. So it is totally independent of the underlying OS thread, even when we call the join method here. So we saw that once we get all the virtual threads for concurrent validation, enrichment, and persistence, then and we call this join method, right, to have all these 3 operations done in parallel. But still, it was not entailing any OS level blocking. In effect, the OS threads jump from code to code when using higher order methods on futures, and they do so in a familiar programming style. You have seen that even the design that we have created is very, very simple, and it's not even having any complexity as we have done in the previous examples with futures. And because these are lightweight, virtual threads are also cheap to create and don't need to be pooled. So we can never pool any virtual threads. I mean, although there are some APIs available, but it's ideal in this scenario that we don't create any pool. We don't want to cap our throughput because we just let it the virtual threads. I mean, that we can create a lot of virtual threads and just rely on the API which has been provided to leverage on that. Okay, so we already done it. Now we have got into the throughput. Although the latency has been not, we can improve by just running a lot of things in parallel, right? So this is what we saw, that although we can reduce the latency from 6 seconds to 4 seconds by running some of the operations in concurrent way, but still it's always better to use futures. So to further break it down from 4 seconds to 3 seconds. So for there, virtual threads as such cannot be that helpful. Virtual threads is only that that can improve the throughput, but not the latency. But still, what we can do is that we can combine the virtual threads along with the futures to improve both the latency. We already seen that using virtual threads, we can improve the throughput by getting many number of virtual threads and handle the client requests at the same time. And by using futures, we can also further improve the latency from 4 seconds to 3 seconds. So this is what we are going to see in our next video, where we'll see that virtual threads with futures OMS, we can use this and further reduce the latency from 4 seconds to 3 seconds. So see you all in the next video.